Thank you very much, and many thanks to the organizers for the invitation. It's always a pleasure to be here. So perhaps in retrospect I should have changed the title. I'm hardly going to present a complete theory today. I just want to indicate some recent progress in some aspects of relative integral p-adic Hodge theory, which form part of a joint ongoing work with Takeshi Tsuji. So to set up the framework, we have some field C, such as the p-adic complex numbers, or more generally, any algebraically closed complete p-adic field. But one really loses no loss of generality, loses no generality if you imagine this to be the completion of the algebraic closure of QP. Inside that, we'll be interested in its ring of integers. And then we have the residue field little k, which is some algebraically closed field of characteristic P. And of course, in this main case of the completion of the algebraic closure of QP, that's then just FP bar. So the type of problem that we're interested in this geometric p-adic Hodge theory is very informally, we want to study, we're going to have some schemes, some varieties over C, over O, over this residue field K, and we're going to look at their various cohomology theories. So if we have something over C, then we'll be mainly interested in its étale cohomology. If we have some scheme, if we spread this out to some scheme defined over the ring of integers of C, then we can look at its de Rham cohomology over O. And if we then take the reduction of this down to, when we look at the special fiber, we get some variety over an algebraically closed field of characteristic P, and then we'll be interested in its crystalline cohomology. And the integral of the title refers to the fact that we'll be interested in the integral forms of these cohomologies. That is to say, we'll be interested in ZP étale cohomology rather than QP étale cohomology. We'll be interested honestly in the de Rham cohomology relative to O without inverting P. And we'll be interested again in the ZP valued form of crystalline cohomology rather than inverting P as one often does. And the relative refers to the fact that eventually lurking in the background, the sort of problem that we'll be interested in is, in fact, we'll want to study some morphism of such schemes, and we'll study the behavior of these cohomologies in families as we vary through all the fibers. So that will be somewhat hidden today. So as typically in p-adic Hodge theory, the story starts by introducing some long list of period rings. But we only need one today, so I've got to write it down. And I ask your patience, if you haven't seen it before, just to stare at it for a moment, and then I'll give you some properties of it, and to not stop listening at this point. So this is Fontaine's infinitesimal period ring, defined as follows. So I'm going to take the Witt ring of something, and that something will be the perfection of O mod P. So O mod P is this ring of integers inside C, so P does not generate its maximal ideal, because there's lots and lots of ramification here. So this is some ring containing lots and lots of nilpotents. We pass to its perfection, that is to say I take the inverse limit over f goes to f to the p of this ring.
It's not what usually means by perfection.
You can take perfection in two directions. I don't think there's a convention as to which one's called what. And this is what in terminology these days is called the tilt of O. So it's some big perfect ring of characteristic P, and then I take its P-typical ring of Witt vectors. And our favorite element inside here today will be the following gadget. So there's two epsilons. So I take the Teichmüller lift. I need to give you an element in this perfection. That is to say, I need to give you some compatible sequence, some p-power compatible sequence. And so I just take 1 comma zeta p mod p, and then zeta p squared mod p, and so on and so forth. That, as I say, is some element of O mod PO. Perfection. I take its Teichmüller lift to the ring of Witt vectors, and I call this epsilon. So here's some structure. So firstly, since it's the ring of Witt vectors, I have a Frobenius on it. And then I have some maps. So let me tell you about the less obvious maps. I have a couple of surjections out of this. In fact, both these surjections are going to have the property that they send epsilon down to 1. And in some sense, we'll be interested later in distinct behavior as to what happens whether we are interested in the locus where epsilon is equal to 1 or whether we're away from this locus. So this is some behavior about the locus where epsilon equals 1. So I have a map from this down to the ring of Witt vectors of this perfect field of characteristic P. So this is well-behaved object. This is just some discrete valuation ring of mixed characteristic. And that map is induced by just the residue field map from O to K. If you like, I have the residue map from O to K. That induces a map mod P. It induces a map on perfections. Perfectifying the right side doesn't change it because it's already a perfect field. And then I take Witt vectors everywhere. And just by functoriality, I get such a map. And then trickier one, very classical, is that there's also a way to surject from this infinitesimal period ring down to O. This is called Fontaine's map of p-adic Hodge theory. I don't want to define it except that it exists, and I give you the one property about it, which is it's classically known that the kernel of this map is generated by the following element. I look at epsilon minus 1, I divide it by epsilon to the 1 over p minus 1. That gives me a non-zero divisor of Ainf, and it's a classical fact that if I mod out Ainf by this non-zero divisor, I get an element, I get O. And just to have the notation, that's usually called Xi. So eventually this whole construction later in the talk is going to be sheafified, and we're going to look at some modules over some sheafified version of this construction. But let me start with the base case now without sheafifying. This is a definition due to Fargues. So a Breuil-Kisin-Fargues module, let's maybe say over O to eliminate any ambiguity, is the following data. It's a finite free module over this period ring. Let's call it, in fact, let me call it non-bold M, otherwise things will get confusing. Some finite free module over this ring together with a Frobenius semilinear map, which is an isomorphism except for possible behavior along this map. So such gadgets are closely related to vector bundles on the Fargue-Fontaine curve. And the primary goal today is to define some relative version of this notion. So we'll eventually get to some notion of a Breuil-Kisin-Fargues module over X, where X will be basically any O schema. Well, to be more precise, I'll take it to be any, well, let's say smooth. In fact, it's going to be a formal scheme, but let's just imagine for the moment that it's some O scheme. So we'll be extending this definition from the case of O itself to any scheme over it. So what can one do with a Breuil-Kisin-Fargues module? Let's have this Frobenius too. So using these maps, so let's recall that the goal is somehow to say something about étale, de and crystalline cohomology. And the first hint that this is possible using this machinery of Breuil-Kisin-Fargues modules is that, so if I have one with some operations we can do to it, I can tensor it through this map down to O, and I'll get some finite free O module. Or I can use this other map base change it down to W of K, and this will be a F crystal. Because it's equipped with, I mean, this Frobenius will induce a Frobenius after this base change. The original Frobenius was an isomorphism after inverting psi, and you can check that this base change has the property that it sends this element psi to P. So the Frobenius that I get induced here will be an isomorphism after inverting P. Maybe this is rather, I'm never sure whether this should be called an F crystal or an F isocrystal. It has an integral structure, but the Frobenius is an isomorphism after inverting P. It's an isocrystal, even though it already exists integrally. It's more data, though, than the actual isocrystal.
No, it's not. Because it's part of the definition of an isocrystal that says a lattice which is stabilized doesn't come.
No, but the lattice is not usually part of the definition. The existence is.
Or you put the lattice in the definition.
So this gives some behavior about what happens when I kill the class of epsilon minus 1. One can alternatively look at the opposite extreme. We invert epsilon minus 1, and then we pass to the Frobenius invariance. And this will give me a finite free ZP module. And more generally then,
is such that indeed it always gives finite free ZP module.
of the same rank, yeah.
Okay.
That's, yeah. So as I said, this is the classical situation of Breuil-Kisin-Fargues modules themselves. And more generally, our goal, once we've got some notion of Breuil-Kisin-Fargues modules on X, I will define some functors that take such a gadget, which I've not yet defined, and from such an object, we'll be able to construct vector bundles on X equipped with a flat connection. Well, I'll follow the, I'm not sure, F isocrystals on the special fiber and lisse ZP sheaves on the generic fiber. So let me explain what's going on here. A single Breuil-Kisin-Fargues module to be defined will simultaneously encode the data of a vector bundle on this scheme over O and the data of an F crystal on the special fiber and the data of a lisse ZP sheaf on the generic fiber. It will be a single object that wraps together three of these such objects and sees some relation between them.
So you wrote XP, so you don't want a linear structure here? I mean, as opposed to the discussion earlier.
Well, I was following then your advice for the terminology. No, this will come with an integral structure, and the Frobenius will be an isomorphism after inverting P.
And
So that means there is something on the not on XP, on the one. Well, it doesn't matter. I will see that. I will ask later.
Okay. It's time to play with her. And we can even do a bit more. So as I've said, a single one of these objects is supposed to simultaneously wrap together some vector bundle with integral connection, some F crystal, and some lisse ZP sheaf. And then we can also wrap together the three respective cohomology theories. So I don't think I'll say anything about this today. A capital K. No, this is a little k. This is a little k. Sorry, should I make it a little bit curly? That would be the... Is that how it's supposed to? Is it clear? So I don't think I'll have time to discuss this today. This is some extension of the earlier work with Bargev, Bhatt, and Peter Scholze, which can now be seen as the special case of the trivial Breuil-Kisin-Fargues module on X. What that means will become clearer once I define these gadgets. And states that, so if I take X proper smooth, again, I could take it to be a formal scheme instead, but let's just take it to be proper smooth honest scheme. O and M, one of these objects, then there exists a complex, even a perfect complex, of modules over this infinitesimal period ring of Fontaine. Let's call it R gamma. It's some cohomology theory with coefficients in M, such that, so this will somehow simultaneously encode the three cohomologies going on here. So let me give some piece of notation. So if I have one of these objects, as I say, you're supposed to think of it as simultaneously wrapping together some vector bundle with integrable connection, some F crystal, and some lisse GP sheaf. And then the theorem says that you can build a single cohomology theory which simultaneously sees these three. Wow, maybe I just got it for Frobenius invariance. So let me.
You have to invert sign.
Here I should have inverted. Here I should have inverted epsilon minus 1 before passing to Frobenius invariance. Yeah.
And all of this is in the derived sense.
All of this is in the derived sense. So let me just summarize the statement. I mean, rather than looking at these statements in the derived category. Thank you. Wrap together, okay, that's a rather imprecise statement. Let's say encode these into a single object gamma xm.
Which is also a perfect complex.
It's also a perfect complex. It's a perfect complex equipped with a Frobenius after inversion of xi. It's a sort of derived Breuil-Kisin-Fargues module. So we'll eventually have some in fact, as I say, I probably won't discuss this today, but the point really is that once you have this notion simultaneously interpolating vector bundles, F crystals, and lisse ZP sheaves, then one can also define a cohomology theory which interpolates respectively the RAM cohomology of the module with connection, the crystalline cohomology of the F crystal, and the étale cohomology of the lisse ZP sheaf into a single object, which then lets you understand how they relate to one another. But what I want to focus on today is just the definition of these objects and how you define these types of specialization maps. So let me set the scene again. So X is now smooth, and I really will take it to be a formal scheme now. And to save a little bit of notation, I write normal X for the generic fiber. Since I now have a formal scheme, I mean generic fiber in the sense of Reynolds. This is a rigid analytic space, rigid analytic variety over this p-adic field. One then associates with this rigid analytic space some pro-étale site, which I'll say a few words about in a moment. So these go back to Scholze's 2013 work on p-adic Hodge theory of rigid analytic varieties, and the definition of the pro-étale site has undergone many modifications in the past 5 years. But for what I have to say today, some other precise version that you work with is not too important. So objects in this, they're roughly towers of finite étale covers of some piece of X. Or more precisely, so they're co-filtered limits, say along finite étale surjections of rigid analytic varieties which are themselves étale over X. So here's a typical example of such a tower. I've got X. I look at something étale over it, maybe a little open, and then I allow myself, they call that one U0. And then I'm allowed to pass to some infinite tower along finite étale covers. So here are two such examples of how you might construct such a tower. So if I took, for example, let's take some open piece. So I take some spur R to some open aphenoid inside X. And then if I want to form such a tower, I can just successively add to the ring R many p-power roots, so of certain units. Because extracting p-power roots of units in characteristic 0, this gives me a finite étale cover. So I can take, as I say, UI to be the aphenoid corresponding to R adjoin P to the ith roots without being too precise of certain units. And in general, as I extract then more p and p-power roots, I'll get such a tower. And what's important for the theory is that if I take the limit of these rings as I go up the tower, so I allow myself to add more and more and more and more and more p-power roots, for example, and then I p-adically complete the result of these, I didn't give them a name, then what I'll get typically will be a ring with sufficiently many p-power roots and will be sufficiently p-complete that this will be perfectoid. So this is the sense in which in this pro-étale site you have many towers for which the resulting object at the end of the tower is perfectoid and thus controls the behavior of this rigid analytic space through perfectoids. That's what's lurking behind the machinery. So that, as I say, is one way to construct such a tower. But then you could also do something much easier. I could just take some open inside my formal scheme, pass the generic fibers everywhere, and then look at the silly tower in which I don't do anything. And this underlies the fact that I've got some projection morphism of sites from the pro-étale site of this generic fiber down to, let's say, the Zariski site of the formal scheme. So to understand this construction of Breuil-Kisin-Fargues modules on X, there are really only 2 points that you need to assimilate. The first of them is this, that I have some sort of étale site of the generic fiber, and I have some projection morphism like so. So you can somehow forget about the formalism, just remember that. And then the second point will be coming in a moment. Let me get rid of this, because it's not going to play any role.
But the definition of coverage family is technical.
Yes.
And it was not quite okay.
Yes.
So it's kind of, and then there is a Morrison thing where it's just like arbitrary limit.
Yes.
And then it's not,
yeah.
You don't get into.
Yeah, and then more generally, you can go all the way to, some V site. But then even beyond the pro-étale site, you've got its V site.
Okay.
But as I say, somehow what I want to say is sufficiently robust that you could work with any versions of these pro-étale site. two sheaves. So let me define for you a couple of sheaves on this pro-étale site of the generic fiber. Let me give this thing a name. So as I say, this is a typical tower, at least in the countable case. This is a typical object of the site. So if I want to define for you some sheaf, I need to tell you what it does on that. And so the first of these is OX plus. So I'm going to clear these are going to be some sheaves on pro-étale site. And so this gadget OX plus, it takes a tower like follows, and it sends it. I just run up the tower, and at each stage I look at the power bounded functions on the ith step of the tower. So on a rigid analytic space, I have the classical sheaf of functions that was studied by Tate, and inside it you can look instead at a smaller subring of functions, namely those which are power bounded, so whose valuation at every point is less than or equal to 1. So the bounded functions on your rigid analytic space. And so I run up this tower. At each stage I look at the functions which are bounded in this sense, and I just take the limit of them as I go up the tower. And that gives for me this sheaf OX plus on the pro-étale side. And then, as I promised at the beginning, we're going to sheafify the construction of the infinitesimal period sheaf. Let me write it the other way around. So I take OX plus, I look at it mod P in the sense of sheaves. That's some sheaf of FP algebras. I perfectify it in the same way as before. That is to say, I take the inverse limit over applications of f goes to f to the p on this FP sheaf. That gives me some sheaf valued in perfect FP algebras. And then I just apply the width vector construction everywhere. That's some, honestly, that's a pretty big object. And that's what we call the infinitesimal period sheaf on this rigid analytic space. So as I promised, there were just 2 points you need to assimilate to understand the definition. One of them is that I have this projection map, and the second is that I have some nice sheaf of
Now, when you compute it, you have to do it in the sheaf sense. So if you are on imperfect, if you take the quotient, it's maybe only a pressure, but you take the sheaf.
That's right, and that causes, yeah.
So even to compute it on the perfect, it's not clear O plus mod P O plus.
That's right. It's not clear, that's right.
Okay. So you do it, and it doesn't give the same answer as you did.
On a perfectoid, it does in fact. I mean, the p-adic completion of OX plus on a perfectoid will give you the perfectoid ring. That's not trivial though. You need to do some work.
Yeah, I'm asking whether the perfect, the plus mod P plus is the value, is the sheaf on perfectoid.
So if the OX
plus modulo P O plus on the perfectoid object
gives you the ring mod P.
Is it the ring mod P?
No.
No. So
but as you pass over powers of P, it gives you the same pro system. So I can re-ask your question for any power of P.
Yes.
And for no fixed power of P will you have this isomorphism. Yes. But the two will agree as pro systems. Yes. The difference between them will be essentially 0. Yes. And therefore when you pass to the limit and complete everything as implicitly happens, then you really will pick up the value of the perfectoid ring. I mean, this is all found in Scholze's 2013 article. Okay. Now I can give the definition. Oh, I think I said over before, so okay. Breuil-Kisin-Fargues module over X is a locally finite free So we start by just mimicking Fargues' definition, and I'm going to take some locally finite free sheaf of Ainf X modules on the generic fiber equipped with, again, I have a Frobenius, and I allow myself some Frobenius semilinear map operating on M, such that, so firstly I mimic the case of the point, namely that phi M, I want the only pole to be along the kernel of Fontaine's map, so I ask that phi M be an isomorphism after inverting psi. That's somehow not the interesting point. Now, I want to emphasize that if I stopped here, it would be dumb. Because in particular, nowhere in the definition has one seen the formal scheme. All the action so far is only taking place on the generic fiber. I'm just looking at certain modules on the pro-étale side of the generic fiber. Now one needs a condition which imposes which somehow witnesses the fact that what's going on the generic fiber is partly controlled by our chosen model. And one asks the following. So I asked that modulo this element epsilon minus 1, which has already appeared several times. I asked that everything is controlled by the formal scheme. So imprecisely, let me say that this comes from the formal scheme. And let me now make this precise. Let me maybe let's just go up there. So here's what I do. Let me reformulate the sentence. So let me restrict everything down to the formal scheme itself. Now, in general, if I've got some vector bundle over some sheaf of rings, and I restrict it in this fashion, then it need no longer be a vector bundle, because I allow myself fewer opens when I do this. And I may no longer have enough opens here to detect the local freeness of some sheaf coming from there. But in fact, I demand that this is not the case modulo epsilon minus 1. So after restricting everything down to the Zariski side of my formal scheme, I demand that modulo epsilon minus 1, I'm still locally free. And that moreover, the action down on the formal scheme completely determines what's happening on the pro-étale side, modulo epsilon minus 1. So that is to say that the base change map back, whoops, should be an M. Is an isomorphism. So this is why I summarize it simply by saying that modulo epsilon minus 1, I'm coming from the formal scheme. I come from some vector bundle on the formal scheme over the sheaf of rings. So I need to include for the sake of honesty, I have to include the following remark, that what I've written is not 100% correct. In fact, it's it's 99.9 recurring % correct, in the sense that it's almost correct, in the precise sense of Faltings almost mathematics. Sorry? So here I could replace epsilon minus 1 by any element. I mean, if I replaced epsilon minus 1 by 0, then I'd really be saying that M came from the formal scheme. If I replaced epsilon minus 1 by any multiple, I get a stronger condition. If I replace epsilon minus 1 by any divisor, I get a weaker condition. And so what I ask, in fact, is that we actually only ask, I don't know how to spell ask, for the weaker condition but which I say is in fact almost equivalent that this holds not for the element epsilon minus 1, but for the element epsilon minus 1 divided by epsilon to the 1 over p to the r minus 1 for all r bigger than or equal to 1.
And there was also a question, as far as I remember, whether you can say a finite projective volume instead of locally free.
You can.
Yeah.
Now I know the answer to your question.
So, because then the notion is stable and the direct.
Yes, so a direct sum of such a thing is still such a thing. Yeah. I could instead ask that it be locally finite projective. If I write locally finite projective, then they turn out to be locally finite free.
Because the rings are kind of local in the sense of...
Actually, I'm not even sure that the rings are local at the level of the pro-étale side, but the behavior is sufficiently determined by what goes on the formal scheme, and there everything is really locally ringed.
Okay.
Okay, this is a remark that I don't want to say so much more about. So this gives you some family of elements inside Ainf, and in some sense when you take the limit over this family of elements, you almost get epsilon minus 1, but only almost. And so if I only demand this weaker condition for all r's, then you can't quite deduce this condition, but you can almost deduce it. And in fact, due to some applications of Faltings almost purity that appear throughout the entire story, it turns out that this slightly weaker condition is the one that you want for the, otherwise the theory doesn't work. I think it's that one. So the advantage of the definition is supposed to be that once one has accepted and assimilated the machinery of the pro-étale site, it's relatively straightforward. And so I want to say a couple of words that it encodes previous work in the subject. So firstly, in the case of a point, so let's say if I just look at spec, or rather spurf of O itself, and I apply this general definition of a Breuil-Kisin-Fargues module, then this is equal to usual Breuil-Kisin-Fargues modules over O in the sense of Fargues. So if you look at the new definition, I need to give the pro-étale side of the generic fiber is now a rather trivial thing because there's no interesting finite étale covers of my algebraically closed field of characteristic 0. So in fact, I just need to give you such a vector bundle, I just need to give you an Ainf module. And then I need to ask whether it satisfies this triviality condition modulo epsilon minus 1. But again, since I've got no covers on the pro-étale side, and I've not got any interesting covers on the Zariski side. This is in fact an identification of sites, and there's no condition being imposed. So this triviality condition just collapses in the case in which there's no étale covers. Let me tell you what these things look like locally. So if you want to discard the formalism of the pro-étale side, here's a local description of how these types of gadgets look. So let's suppose, well, let's take some affine open spoof R inside X. So here R will be the p-adic completion of some smooth O algebra. And then, as usual in Faltings' approach to p-adic Hodge theory, one looks at various associated universal extensions. So let me begin by inverting P and passing to its universal cover. So by this I mean the following. So this, as I say, is some extension of R1 over P, which after taking specs would really correspond to a universal cover. So this is maximal ind finite étale extension of R1 over P sitting inside some fixed algebraic closure of the field of fractions of R. So the Galois group here is precisely the étale fundamental group of R1 over P with respect to some chosen base point. And let me call this curly R. So this is some geometric fundamental group. I mean, let's think about what's going on the generic fiber. My generic fiber is some variety over a characteristic zero field. This corresponds to some open piece of it, and I'm looking at the geometric Galois group of this open piece, of this affine open of some variety in characteristic zero. And then inside I've got R, and I can pass to R bar, which is just the integral closure of R inside R1 over P bar. So this is now some extension which is highly ramified at P. I could, for example, be adding lots and lots of P power roots of certain units in here, and these give me lots and lots of ramification at P here. My geometric Galois group is still acting. So we have this general definition of Breuil-Kisin-Fargues modules on any smooth O scheme. So let's look at how these things look on this open piece. And in fact, this notion of a Breuil-Kisin-Fargues module on X, it behaves well under gluing. So if I tell you how it looks on all the opens, then in principle you can glue it to get the notion on the whole scheme. Finite projective. So to give you Breuil-Kisin-Fargues module on this open, I need to give you a finite projective module M over the Ainf period ring of this type of gadget. So that means so there should be a bar there. So this is by definition the usual construction. So R bar is some massive ring. Modulo P, it will contain lots and lots of nilpotents. So I perfectify it to get some perfect ring of characteristic P. I take its width vectors. Then I'm going to look at finite free modules over this. equipped with, well, let me write it informally, a Frobenius satisfying the same properties as before, that it's isomorphism after inverting psi, and equipped moreover with a semi-linear continuous action by this geometric Galois group which is trivial modulo epsilon minus 1. In a similar sense to the previous definition, so I've got this action of this group, and I ask that once I go modulo epsilon minus 1 and I pass to the G invariance, this is big enough to determine what's going on.
And also you have to correct it epsilon minus 1 divided by.
And the same previous remark applies that one actually needs the finer, almost equivalent definition. And this functor then is given, as one might expect, by taking, so I've got some pro-étale, excuse me, I've got some vector bundle on the pro-étale site over this period sheaf, and I just evaluate it on, I don't have space for it. Well, let me be kind of dirty and just write sperf R1 over P bar. Sorry, spacing has got very bad here. This is a bit of a lie. The point is that this big ring R bar will determine for me some athenoid perfectoid object inside the pro-étale site of X, and then I can just evaluate my sheaf of rings on it. And so it's just some, I mean, at the end of the day, it's just saying that certain vector bundles are determined by their value on some cover together with the Galois action describing this cover. In that sense, it's not a surprising result. The subtlety is that there is no good theory of vector bundles over this sort of bounded sheaf of functions on rigid analytic spaces. So if you study locally free sheaves, let's say over OX plus on some rigid analytic space, and you evaluate it on some athenoid open, then the sections will not necessarily be a projective module. And the H1s will not necessarily vanish. So all of the usual methods that you would use for checking this type of correspondence break down, but they remain almost true thanks to some applications of Faltings' almost purity theorem, and then there's a lot of work that goes into controlling all these almost obstructions that appear. And the appearance of all these almost obstructions is the reason for this remark that you can't quite impose this epsilon minus 1 condition, because this equivalence would in fact not hold if you worked with the epsilon minus 1 condition rather than the almost equivalent condition. You'd lose control over.
And for the G action being trivial, so you have to implicitly have to know what the ring mod epsilon minus 1 divided by something.
Well, I don't even know it. I look at the G invariance of it.
And you have a description of the G invariance.
Yeah, one does in fact. Yeah. It will in fact just give me various rings of width vectors of R.
And again, the condition is risky local. Okay, maybe it's...
No, here, I mean, at least, I mean, I recall, I think you raised this issue in Japan as to whether one needed R to be small, but I really don't think that's the case.
Okay.
I mean, maybe then there's no interesting geometric Galois action, but then the theorem would just become trivial instead. So I wanted to put some names on the board. So these types of gadgets, that is to say, representations of these geometric Galois groups on modules over suitable period rings of perfectoids, these were introduced by Faltings under the terminology of generalized representations. And they were quite extensively studied in the book. of Aves, and Tsuji on Faltings' p-adic Simpsons correspondence. Some manifestation of them appears there. But what we have now is a reinterpretation of them in terms of the pro-étale side in an integral fashion. So I feel I should explain to you, since I have 5 minutes, something about this diagram. So I promised that from such a Breuil-Kisin-Fargues module over X, there'd be some method to construct vector bundles equipped with a flat connection, crystals, and lisse ZP sheaves on the generic fiber. And I should tell you how at least one of these goes. Let's bring that one down. Play back one. By the time I get the board ready, the time's going to be over. So the ideal goal, I don't have time to do all of it, is given some such object on X. So I say we're supposed to be able to construct a module with integrable connection, a crystal with Frobenius, and a lisse ZP sheaf. And I think I'll just do the Duram and then say a few words orally about the others, but the Duram is relatively, it's okay. So as I said, great, the definition is still there. So I have this notion of m mod epsilon minus 1 coming from the formal scheme, and I mentioned that I get a weaker condition if I replace epsilon minus 1 by anything dividing it. That's purely formal. So in particular, this holds if I replace epsilon minus 1 by epsilon minus 1 divided by epsilon to the 1 over p minus 1. Which is this element psi that's been floating around a little bit. And so the hypotheses tell me that modulo psi, if I then restrict down to the Zariski side of the formal scheme, this is a locally free sheaf of modules over my ring mod psi. So I say that's just by taking this mod psi instead of mod epsilon minus 1. We also have a Bockstein sequence, so I can look at m mod psi, I can look at m mod psi squared, and m mod psi again, where this first map is given by multiplication by psi. So this psi is a non-zero divisor on this sheaf of rings, m is a vector bundle, so it's still a non-zero divisor on that. I formally get such a sequence. And I know that these exterior terms, by my triviality hypothesis, come from the formal scheme. true for this, and this exterior term. So let's now restrict everything to the formal scheme. What do I get? I get an associated boundary map, that is to say Bockstein, coming from the restriction of M mod psi and going to the R1 nu lower star of this, which will be using this formula just given by the nu lower star of M mod psi tensored up by nu lower star of A mod psi of R1 nu lower star of A mod psi. That is to say, to compute the higher direct images of M mod psi, I only need to know what it's doing on A mod psi, because everything else is just a stupid base transfer of that by some finite free module. And one now uses some standard calculations in p-adic Hodge theory that if I take this period ring A mod psi and I restrict it down to the formal scheme, I don't get something mysterious, I get the structure sheaf on the formal scheme. And what about the next higher direct image? Well, at least if I kill the P, in fact, if I just kill the P torsion, it will be sufficient. This higher direct image could have some P torsion, but if I kill this P torsion, well, I get some sheaf of modules over this, i.e. some sheaf of modules over OX. What is it? Again, standard calculation in p-adic Hodge theory tells you that it's just the first sheaf of Kähler differentials on your formal scheme. And so now we can read back through what I said a moment ago. The push forward of M mod psi is some locally free sheaf over OX, and it's equipped with some map to itself tensored to omega 1. That is to say, it's a vector bundle with flat connection. At least if I kill the P torsion on the right-hand side, but I can do that. And one, of course, one needs to check that under these identifications, the Bockstein really does give you a flat connection, but that's some local calculation that one can do by hand. So I better finish there, and I better finish there, in fact. Thank you.
Thank you very much. Is there a quick question?
I can repeat the question if it's not loud enough.
So could you also use the geometry of the Fontaine-Fargues curve in describing all these objects?
I don't know. If you discard this type of integrality condition, that everything mod epsilon minus 1 is determined by the formal scheme, and you really just look at locally free Ainf modules equipped with the Frobenius, I mean, that's then really what Fargues is systematically studying these days. These really do correspond to vector bundles on the Fargues-Fontaine curve, and this corresponds to some stack of vector bundles on the Fargues-Fontaine curve, in fact. But once one imposes this extra integrality condition, which is really necessary in this story, I don't know how to interpret it in terms of the Fargues-Fontaine curve.
Oui, I don't mean so much, but if we look at, if we have an isocrystal on the multiple reduction of your formal scheme, we do not know in general that there is a vector bundle with a connection on the formal scheme. What we do know is that there is a vector bundle on the characteristic zero fiber, and there is an extension as a coherent module with a connection on the model, but we don't know we have a vector bundle. But here, so that means you don't, since we don't know that, possibly you do not get all the isocrystals, but only those which have a locality extension. Right?
Yeah, I would not be asserting that one hits every crystal on the special fiber in this way. No, no.
And this is hidden, it goes too fast for me, but isn't it hidden in the definition you have? You P, K, F, spec, F, R. You start with the projective finite modules from the scratch. I mean, they are not projective finite modules. Yeah, they are really projective finite modules on the whole model, not only on the characteristic zero fiber.
I'm not sure I follow the question.
Okay.
Okay.
Maybe you can discuss this later. Okay.
Okay.
Very quick.
Yeah, okay, no, I just, so you have your sheaf M and you associate to it the Raman fellow, you have locally, you have this sheaf associated to it. How one to this?
Yeah, this is a very good question that I don't know at the moment. I mean, so if you invert P everywhere, I mean, this is the integral story, but if you invert P...
I suppose, so you know it's 1 to 1.
Well, no, because I'm working over some infinitely ramified base. So even that's not clear. I'll tell you my musings afterwards. Well, rationally it should... I mean, you're right that rationally you should be able to discard the information of the module integral connection. It should be more or less determined by the behavior on the special fiber. And then you should recover Faltings' notion of an isocrystal on the special fiber being associated to a QP sheaf on the generic fiber.
You didn't know whether
Yeah.
But what I'm saying, if you compare it with the Deram association, then you would know it's in. I mean, the sense of choices, Deram sheaves.
Ah, okay, like over OB Deram. Yeah, that should determine everything that's going on after inversion of P, yes. Yes.
So we need to thank the speaker again and we resume in 5 minutes.